Hey everybody, we're going to go over 5.3, which is going to go over graphing of exponentials and of logarithms. So exponentials have a pretty easy pattern to follow. It all just depends on the base. I'm actually going to start with question number 2, and then I'm going to jump back to question number 1. So I'm going to start with question 2, because I want to start with a base like this one right here. So for exponential models, functions, y is equal to a times by b to the x power. I don't think we're going to see too many models here. I don't see any right now anyways, where we're going to have an a times by b to the x. But if we did, this a right here would be, it's pretty much just like the stretch or the shrink. It's pretty much just like a stretch or shrink. But it also has a role in exponential models where it's also going to be used or called and referenced as the initial amount. The reason being is if your exponent is equal to 0, so if you're trying to plug 0 into an exponential model, well, b to the 0 power is going to be equal to 1, so what you're going to be left with is just a. Now, in that case right here, so most of our models, if not all of our models that we're going to be practicing, will just be y is equal to b to the x, meaning that our initial amount should always just be 1 for the most time. And as for the parent function, the initial amount is always 1. What this means for us is that exponential models, at least for the parent functions, so for this model right here, y is equal to 3 to the x, the initial amount is always 1. So the y-intercept is always going to be 1. Okay? Now, depending on the base, that's how you're going to create your pattern for graphing. So if b equals 2, this means that the model will always be doubling. So the model always doubles. If b equals 3, then the model always triples. So let's just say, for example, let's say that we have, I'm going to graph, no, do I have an empty blank graph? I think I do down here. I'm just going to draw it here just because we have blank space right here. And I don't know why Alex generated 2 graphs right here when it only needs 1. But for y is equal to 2 to the x power, so because it's just a model of b to the x and not times a times b to the x, our initial value is going to be 1. And then we're going to double that. Well, what's double of 1? It's 2. What's double of 2? It's 4. Double of 4 is 8. Double of 8 would be 16, and so on and so forth. So that's what I mean by these models right here. Really, the rate of growth depends on the base, and so on and so forth. Now, I guess to talk really quickly, what happens to the left side? How do I draw the left side? Well, if you're starting here and you're always doubling, that's what it's going to look like. But if you're trying to think in the reverse direction, so when x approaches negative numbers, it's not doubling, but it's always cutting by half. And so that means that it would be a half. And then a half of that would be 1/4. A half of that would be 1/8. But eventually it just keeps halving, so the number gets really, really close to 0, but never actually becomes 0 itself. And so this exponential model just keeps getting closer and closer to the x-axis. but this would be what the parent function of 2 to the x. Now, each exponential model, if it has a different base, is going to have a different parent function. So if you have y is equal to 3 to the x, okay, here's a model where the initial value is going to be 1, and the base is 3, so that means we're always going to be tripling. So that means when x is equal to 1, it's going to be 3, because that's what, if you triple 1, that's going to be 3. And if you triple that, that's going to be 9. And then if you triple that, that's going to be 27. But that's what your model is going to do right there. And then before that, you're not going to be tripling, but you're going to be cutting it by a third. So what's a third of 1? Well, that's going to be 1/3, and then you a third that, and so on and so forth. But it goes like that right there, and it will just get closer to the x-axis. And then if you had something like y equals 4 to the x, when y is equal to 4 to the x, the initial value is still going to be 1, but the values afterwards are going to be quadrupling. So that's going to be at 4. And then the next after that is going to be 4 times 4 is going to be 16. So it's going to be far up there, but it's going to be quadrupling. And then to the left of that, it's going to be not halving, it's going to be dividing by 4 each time that for each unit that you go down. So it's going to be a fourth, and so on and so forth. But in any case, that's what we're dealing with with exponential. So I'm going to come back to this drawing actually when we go to question number 1. But let's go back to question number 2. So we're going to take a look at our exponential model. Our exponential model is 3 to the x. So our initial value is 1, and then we're going to be tripling. So you can see that that's why there's a point right there. Whenever 6, 7, 8, whenever we get to 9, we're going to have a point somewhere up there. Okay? Actually, I'll just put that right here anyways. Okay. All right. So that is how you graph exponentials. That's the way I like to look at it. Now, let's say that you did have something like y is equal to 2 times by 3 to the x. Well, this would mean that our initial model, our initial value would be 2 instead of 1, and then from there we would just have to triple. And so what's triple of 2? 2 times 3 is going to be equal to 6. You can see that here again, if we plug in 1 right here, 3 to the first power is 3, 3 times 2 is 6. And then you would have to choose the initial value, and we triple it. And we triple that. And a triple of 6 is going to be 6 times 3, which would be 18, and so on and so forth. So if you have a different starting value, then that just tells you this is the number that you will be tripling over and over. Okay, so keep that in mind, but I don't think we're going to see too many functions that have a different initial value other than 1. Okay, so with that being said, here is our graph, and we're being asked to, below is the graph of y equals x, y equals x to the third, translate it to become the graph of y equals 3 to the x minus 1 minus 2. Now these right here are going to be your translation. So x minus 1 is going to be a translation to the right one. And then this right here is going to be a translation down 2. So we're still following the same translation rules that we've been doing all year in terms of graphing. If it's inside with the x, you read it to the opposite, and it's always horizontal left or right. If it's outside, not with the x, it's vertical, and we read it as it is. So negative means down, positive means up, and so on and so forth. So what we're going to do with this graph right here, we're going to take these points. We're going to take this point right here, we're going to take this point right here, and then the point that we had all the way up here, we're going to move to the right one and down 2. So to the right one, down 2. To the right one and down 2. To the right one and down 2. So right here. Now another thing that we kind of neglected to talk about is this, the fact that this graph right here gets closer and closer to the x-axis. This is what we call the asymptote. So this is called a horizontal asymptote. Okay, now horizontal asymptote, it will be affected by translations, but only vertical translations. So changes with vertical translations. Changes with the vertical translation. So what I mean by that is, hey, we're moving all these points to the right one. Well, okay, I guess I can move this line right here to the right one, but that's not going to change the fact that it's still in the same spot, right? But down to, if I take this horizontal line, this can only be, that means that we can actually move this line down too. So the horizontal asymptote will move with vertical translations. So that would mean that this horizontal asymptote will actually be down at -2, which means that we're going to, let's connect our dots, so on and so forth. This line is going to approach that horizontal asymptote. So all we're doing is just taking this graph right here, moving it to the right one and down 2. Okay, should be pretty easy in ALEKS, but that's what it should look like. I think in ALEKS you're just gonna have like some sort of button that allows you to move left, right, up, and down. You'll just drag this graph like that. I don't think it's going to be like that on the test, for what it's worth. I think on the test I'm actually going to have you graph these by hand. So make sure you know how to get these points right here. Okay, now for further explanation, let's go back to 1, because now we have a base of 1/3. Okay, now this exponential model, I guess I'll explain here, but exponential models can either be exponential growth or exponential decay. So if y equals b to the x, if for y equals b to the x, if b is greater than 1, then the model has exponential growth. But then if b is less than 1, but b is also greater than 0, so numbers between 0 and 1, then the model has exponential decay. Okay, so I'm going to go back to those drawings that we had here for parent functions. I'm using these graphs to kind of help us understand the pattern. So I'm going to take, for example, what if we have y is equal to 1/2 to the x? All 3 of these examples are examples of models that have growth, exponential growth. Y equals 1/2. 1/2 is a number that is less than 1 but greater than 0. This is an example of exponential decay, but very simple to explain this right here. The initial value, that a property of the initial value, is still going to be the same. So we're still going to have, I'm actually just going to erase these right here. We're still going to have an initial value at 1. That doesn't change. If this is going to be to the 0 power, anything to the 0 power is going to be 1. But if it's exponential decay, it has the same kind of pattern, but in a way where you should be, where the graph needs to be decreasing. So whenever I think on the right side of this graph, if it's exponential growth, then it doubles. But if it's exponential decay, then that's where it's going to half. So it's going to half, and then it's going to half, and then it's going to half. And so to the right side, it's going to decrease by half. And then for the other side right here, it's going to double on the left side. So it's going to double as the x values go negative. So it's going to double here, double here, double here, and so on and so forth. So basically what it comes down to, and one way to look at it, is that if you have a half to the x power, it's basically just a vertical reflection. It's not a vertical reflection, a reflection across the y-axis. Okay, a reflection across the y-axis. If you had a third to the x, so actually let's go back up here because that's what question number 1 is. So for question number 1, it's 1/3 to the x. So you can see from this graph right here, we have an initial value at 1, and then it's going to be a third, and then a third of that, and so on and so forth. But then if you think in the other direction, it's going to triple. So there we have from 1 to 3, and then from there it's going to go to 9. So 6, 7, 8, 9, so I guess it would be somewhere like right here. But yeah, so those are our points right there. And yeah, 1/3 to the x plus 4. So x plus 4, this is going to mean that we're going to shift this graph to the left 4, and then we're going to move it down 2. So these points right here, I'm going to take this point right here, move it to the left 4, and down 2. So right here, going to take this point right here, move it to the left 4, and down 2. So right here, so on and so forth. You can take this point right here, move it to the left 4, and down 2. So right here. And the horizontal asymptote is also going to be moved down 2. So where the horizontal asymptote would be right here, we would move it down 1, 2 right here, and that's the path it's going to follow. It's going to keep going like that. Okay, one other thing to mention, like I just said, that you can think about 1/3. If it's 1/3 versus 3 to the x, think about it like a reflection across the x-axis. Well, something that's kind of funny is that it's not really, but it kind of is, but it's also equivalent to that at the same time. But y equals 1/3 to the x is the same thing as 3 to the negative x. Okay, so this right here is whenever you take the graph of 3 to the x and you multiply the x by negative, that's a reflection in the y-axis. Well, they'll be the same thing. They'll do the same thing. So these are actually equivalent right here. Okay, these are actually equivalent, and you can think about it with your negative exponents. If you have 3 to the negative x, well, if you have a negative exponent, then you use the reciprocal right here, and then you can see how that's actually the same. So I said it's not really the same, but actually it is exactly the same. But yeah, there you go. So just keep that in mind. That's also equivalent right there. All right, moving on. So let's go to example 3. So example 3, we have the function y equals 4 to the x. We're going to have an initial value of 1, and then we're going to quadruple. So 1, and then to 4, and then the next one would be at 8. 16, because you're quadrupling. But let's just take these points right here. We have these translations. So right here, that means we're going to move to the right 2 and up 3. So right 2 and up 3. So right 2 and up 1, 2, 3. So right here. Okay, then for this point, move it to the right 2 and up 3. So right here. And the horizontal asymptote, this horizontal asymptote, I don't know if it's you have to graph it, but this one's also going to move up 3. 1, 2, 3. So our graph, whenever you move it, should look like this right here. Okay, but yet again in ALEKS, you should just be able to pick this graph up, move it to the right 2 and up 3. Okay, we got another one right here. This one's 1/4 to the x. Okay, well, this is going to have an initial value of 1, and then it's going to be cut into fourths, so fourth, and then a fourth, and then a fourth, so on and so forth. But it's just going to be easier to actually just quadruple in this direction. So you can see that we have a point at 4 because that's, if you quadruple 1, it's going to be 4, and then it will be 16 up there. But let's just take these 2 points that we have right here, and we're going to be moving it to the left 2 and up 1. So left 2 and up 1. So these points right here, move it to the left 2 and up 1. Move it to the left 2 and up 1 right there. And that also means that the horizontal asymptote is also going to be moved up 1. So move that up 1 right here. And our graph should look like that. And that's where it should be when you move it. Okay. All right, for question 5, so we have exponential models. So these are exponential models with the base e. So exponential models, is it going to let me write? Wow, what a delay. So exponential models with the natural base. So remember last time when we talked about the natural base, e is the natural base, and we said e is equal to 2.718, something like that, and it's an irrational number. So that's what the number is right here, which makes it kind of tricky because, again, we said that the base is the number for which it's always multiplying by, right? So that's going to be a little weird, okay? Because it's hard. This is an irrational number, so you can't. It's more difficult to multiply by that by itself right there. But let's just talk about the easiest way to graph these. Honestly, it's just with a calculator. Honestly, because of the fact that this is an irrational number. But I do want to take a look at this expression right here. First, I want to look at this right here. 1 divided by 1/4. That's just going to be equal to 4. So if you see an expression that looks really weird like that, like 1 divided by 1/2 or 1 divided by 1/3, 1 divided by 1/4 is just the reciprocal of 1/4. So 1 divided by 1/4 means the reciprocal to 1/4, which means 4. And so just to kind of put this into more simpler terms, this is equal to 4 e to the x minus 3 minus 4. Okay? All right. And then one thing I guess we can do is the initial value. That's kind of the easiest point to start with. So the initial value meaning when x, so I like to start with the initial value. Initial value is when x is equal to 0. That's probably the easiest point to graph on here because that's the only point that is probably going to give you, oh man, I just messed up. Not when x is equal to 0, sorry. Initial value, let's say that, I guess it is when x is equal to 0, but that's, I'm going to cancel, I'm going to forget about that. But, how should I say this? We're looking to plot a point on this graph right here that's easy. And the first point to kind of plot just without a calculator would be whenever this equals 0. So when the exponent equals 0. So that's going to be when x is equal to 3. That's probably where you're going to want to start right here. So we've got 4e to the 3 minus 3. So basically what I'm saying is the first point we're going to plot for this graph right here is going to happen at x equals 3 because that's what's going to make our exponent 0. So the first point we plot will be at 3. So 4 to the 3 minus 3, then minus 4. So 4e to the 0 minus 4. Now 4 to the 0 power, sorry, e to the 0 power is 1. So 4 minus 4, and so that's going to be equal to 0. So at x equals 3, the output is going to be 0 right there. Okay? I'm trying to, let me see what Alex wants you to show for this problem right here. But I'm assuming that you're just going to have to plot a couple of points. I'm not sure how many points. Let me check and see what Alex says. So plot 2 points on the graph of the function and also draw the asymptote and click graph a function button. So we have 1 point right here. We need to graph one more point. This is where you're going to need your calculator. So you need a calculator for this next point. I guess you can use any points, but the easiest point is whatever makes this equal to 0. So that's going to be for me when x is equal to 3. So just pay attention to what your exponent is. Okay, and then for the next point, it might just be easiest to plug in 4. So to plug in 4 into the function. So that's going to be 4e to the 4 minus 3 minus 4. That's going to be 4 times by e to the first power minus 4. And this is where you're going to need a calculator. So you can use Desmos, you can use anything that uses e as a base, but 4e minus 4, I'm just going to use Desmos really quickly. So I'll go into Desmos, and I'm going to type in 4e minus 4, and I get 6.873. So 6.873. So 6, oops, oh my gosh. My goodness. 6.873. I totally even forgot. 6.873. Yes. Okay, so that means at x equals 4, that's where that point is going to be at 6.873. 6.873. Now, for you, in your Alex, just to kind of help you guys, there's going to be this box that you're going to have to the right side. Wow, terrible box. So you're going to have this box right here. There's going to be a button down here, and it's going to look like a graph, and it's going to have an X right here. So you're going to want to click on this button right here. And then it's going to give you an opportunity to type in a point. So what we're going to do, since we plugged in 4, or since we plugged in this point right here, that meant that we plugged in x equals 3, so we plugged in, oh my goodness. So we plugged in 3 and 0. You actually can probably just plot this point by hand. So probably for that first point, you're probably just going to click on the pencil button right here, the pencil button, and then plot it right there. Or you can do it in this button as well. But for the next point, since it's going to be a little bit trickier to plot that point right there, we plugged in 4 and we got 6.873. Yeah, do not approximate, for example, and not. Yeah, I think that's what you'll want to do. Hopefully that works. I think it should work. Or you know what you could do? Oh wait, no, you don't want to do this. Just kidding, you don't want to do this. What we could do is just type in 4e minus 3. So type in 4e minus 4. That's probably what we're going to want to do right there, is just type in 4e minus 4, the same thing that we got when we did it by hand. So whenever you do that, then you'll be able to hit this button right here, the button that shows up right here, and then that will put a line through your graph right there. And then what we're going to have to do, so let me go ahead and put this point right here. So 6.873, so something like this right here. And it should put a line that goes through your graph. Now, as for the horizontal asymptote, because it's going to require you to graph that, the horizontal asymptote, which was at x equals, or sorry, at this y equals 0, as far as the translations, it was moved down 4. So this has to be moved 1, 2, 3, 4, so it's going to be here. Now, in Alex, what you're going to have to do to graph it, there's going to be a button on the left side that's going to have a horizontal line. This is for horizontal asymptote. So that's what you're going to want to type in. So if you click on that button right there, it's going to ask again, it's also going to ask for a coordinate point. It's going to give you a point or an option to plug something in. Now, because horizontal asymptote moves vertically right here, that means the only value you're supposed to type in is going to be this value. So because it happens at y equals -4, you're going to plug in -4 for this value and 0 for that value. So this is always going to be the case for horizontal asymptotes. 0 for this part right here, and wherever the y value is that it crosses, that's what's going to be the y value here. So whenever you type that in and draw your asymptote, that's what it's going to draw, and your graph should look something like that whenever you finish. Okay, so a lot more goes into graphing these with a base of e. I think we've got one more, so let's go ahead and do that right there. So we've got this one right here. All right, and we've got 2, then we've got x plus 1 plus 2. Maybe we can draw our asymptote first. So our asymptote, which will be right here, it's being moved up 2. So maybe we'll start with that. So that would mean that the asymptote should go here. So that means whenever you're in ALEKS, you got the box of options. Go ahead and click on the horizontal asymptote, and then it's going to bring up a point right here. And we're going to plug in 0 and 2, and that should draw your asymptote. Okay, let me actually do that. And here I have ALEKS pulled up, and I'm going to see if it works. Okay, and then yeah, you should be able to exit that window afterwards, and you should see your horizontal line. Okay, now we're going to plug in 2 points. I always say that the easiest point to plug in is whatever makes this 0. So I'm going to look right here. So that's going to be when x is equal to -1. So when x is equal to -1, I get 2e to the 0, because when I plug -1 in here, -1 plus 1 is 0, and then plus 2. Well, e to the 0 is going to be 1, so 2 plus 2, that's going to be equal to 4. So when I plug in -1, I should get +4. So right here. That's where that point's going to be. Okay, and then we're going to plug in another point. I'll probably just plug in the point immediately after, so I can plug in, do I want to plug in this point right here? I guess I could. It doesn't really matter. Let's see if it works. So 2e to the, 0 plus 1 plus 2. So I'm plugging in 0, okay, and then that's going to give me 2 times by e plus 2. And then I'll just, that's what my value is going to be. So whenever you go into ALEKS, you're going to plot a point. So there's that button with the graph. You're going to click on that right there, and you're going to plug in the point. You're going to plug in 0, because that's what we used for the x. And then we're going to type in 2e plus 2. And you're actually going to see if that works on my end of ALEKS right here. So I would plug in -4, so -4, and then I think I would get 0 if I plug in -2, -3. Okay, that's going to give me 3e minus 3. So plug in -3, and then I'll type in 3e, I gotta click e, minus 3. All right, by the way, whenever you type something in right here, it's going to bring up another little box right here, and it's going to have e, and then it will have your exponent box, and then it's going to have your fraction box whenever you need them. Make sure you click on that to use e. Okay, and then I'm going to check it, see if it works. All right, that's what works. All right, good thing I checked this, or else I would have told you something that wouldn't work. All right, so for me, that would put a point. If I do 2e plus 2, and actually, let me just go ahead and check that here. So 2e plus 2, and I get 7.437. So maybe something like right here. If Notability will work. My iPad is going really, really slow right now. Yep, there we go. And that's what mine will look like right there. Okay, that should be enough of those right there. All right, for question 7, we're going to talk about logarithms. So for logarithms, remember I talked about in the first lesson, we talked about how exponentials and logarithms are inverses of each other. So what that means is, let me go back to, actually I'll just use this space right here immediately above. So let's talk about 2 to the x. So 2 to the x is whenever you have the initial value of 1 and it doubles. It doubles like that right there. So you get this nice little exponential growth model that looks like that. that looks like this right here. Okay, now what we learned in the last unit about inverse functions means x and y values are switched. So whenever I'm going to graph a log, the inverse to 2 to the x is log with a base 2 of x. This is the inverse of 2 to the x. These are inverse functions, inverses. And how do I graph log base 2 to the x? Well, same way that I graphed them in the previous unit, I'm just going to switch these values right here. So this value, which is at 0, 1, I'm going to graph a point at 1, 2. For the next point, which is at 1, 2, I'm going to graph it at 2, 1. And then at 2, 4, so 4, 2. At 3, 8, so 8, 3, and so on and so forth. And so my graph should look like that right there. And this time the graph is going to go this way. So here's what log base 2 looks like. And one thing to note is that the horizontal asymptote for our function is, so exponential models have horizontal asymptotes. They have a horizontal asymptote at y equals 0. Logs have vertical asymptotes because, again, for the same reason, x and y values are swapped. So if the exponential has an asymptote along the x-axis, the logarithm, its inverse, is going to have a vertical asymptote along the y-axis. And that's how you graph your logarithms. They're just inverses of each other. So it's still doubling, but what is actually doubling is the x values are going to double instead of the y values. So the x values double, not the y value. Again, it's the reversal of the x and the y. Here, 2 to the x means you start with 1 on the y-axis and you double in the y direction. Here, you start with 1, the initial value is going to be 1 on the x-axis, but you're going to double in the x direction. So you're going to double your numbers that way. And you follow the same pattern for log base 3. So we're going to, if you need to plot the points for 3 to the x, that's fine. So for 3 to the x, you have a point at the initial value at 1, and then you triple. So at 2, it's going to be 9, so up here. And then for the graph of log base 3 of x, you're going to start with 1 on the x-axis, and then you're going to triple the x values. So from 1 to 3, and then it's going to be at 9 and 2, so out here. So there you go. We have those points right here. That's how you get your logarithm function. Okay? And then what we have here are the translations. So we're going to graph this graph right here. So we have x minus 1. That's going to be a shift to the right one. And this is going to be up 3. Okay, so we're going to take these points out. Actually, first, let's talk about the asymptote. So the vertical asymptote is going to be here for the logarithm. Now, this one, it doesn't matter if you move it up or down. It's not going to change if you move it up or down. But this one's going to change if you move it left or right. So since we're moving this to the right one, the horizontal asymptote will shift right here. All right, and as for the points, so we're going to take this point right here, move it to the right one, and up 3. So right here. And we're going to take this point right here, move it to the right one, and up 1, 2, 3, so right there. Whoops. Okay, and so our graph, whenever we move it, whoops, what did I just do? I have no idea. What the heck is that point right there? Okay, sorry. I erased the wrong points. There we go. So those points right there I'm going to remove. There we go. So our graph should look like that whenever it's finished. Whenever you move it. Okay? All right, let's move on. Oh, I don't want to see you just yet. Let's look at number 9 first before we get into, I'm going to do 8 last. So let's do 9. Okay, so we have a log with a base of 2. Perfect. So what this means is that the initial value is going to be at 1 on the x-axis, and then it's going to double in this direction. So then 2, and then 4, and then it will be at 8, 6, 7, yeah, right here. All right, and then the let's draw in the vertical asymptote. So here's the vertical asymptote. We're going to move it to the, so these are the translations. The translations are going to be to the left 3 and down 4. So that means that this one, yeah, you can move it down 4, but it's not going to do anything. But we do need to move it to the left 3. So 1, 2, 3. Okay, and that also means for these points that I have right here, whenever you move it, you're going to move it to the left 3. So 1, 2, 3, and down 4. 1, 2, 3, 4. So whenever you move your graph, it should be pretty easy in ALEKS, but it should look like this right here. Okay, for 10, we have a log base 3, so the initial value is going to be 1 on the x-axis, and then it's going to triple. So we have those 2 points right there. There should be a point like probably like right here, and these points are going to, that means it's going to move to the right 4, and then down 3. The vertical asymptote right here is just going to be moving to the right 4, so right 4. And same with these points right here. So we're going to move to the right 4, 1, 2, 3, 4, and then down 3, 1, 2, and 3. And there you go. So we'll have our logarithm graph that looks just like that right there. Okay, let's look at the natural log of x. So the natural log of x, the reason why I saved this for last, well, actually, this one should be pretty easy because we don't have to plot points. But remember that a natural log is a logarithm with base e. Log with base e. I'm actually really glad that we don't have to plot points for this one right here, because the points are just annoying because it's irrational. So actually, all you have to do for this one is follow the same rules. Well, so you have a point right here. The first point that's going to be moved over this way, so where it crosses right here, that's the point, this is the point E, comma 1. So that's what this point is right here, E, comma 1, because E is the base of that right there. So you can see for the other ones, the first point over, so this was a base of 3, right, for this one up here, yeah, base of 3, so 3, 1, that's what the first, so you have the initial value, and the first point after is 3, 1. For this one right here, the initial value is 1, the point after is 1, 2. So for the natural log, it's going to be the initial value and then E1, which would be that point right there. And then we're just going to take these values right here, and then this is going to be a shift to the left 4 and then up 2. So your vertical asymptote, which I don't think you have to graph in there, it's going to be moved to the left 4, so it'll be like right there, and these points right here will also move to the left 4, 1, 2, 3, 4, and then up 2, 1, 2. So whenever you move it, your graph should go through those 2 points like that right there and follow the asymptote. All right, but that should be everything you need to know for the graphing. Hopefully that helps. Let me know if you have any questions. I know it's a weird graph, especially for logarithms, but that should be everything.